So welcome everybody. This is the first session of the PRIMO talks. Hopefully the first session of a quite long list of sessions. We are starting today and we hope that we'll be able to maintain a schedule of a talk every couple of weeks, more or less. Hopefully the idea will be to have talk about different topics in optimization, inverse problems, and machine learning, since the PRIMO group is meant. So the idea behind the PRIMO group is to work on the connection between these three areas. So we hopefully will stay tuned with you, and we'll try to let you know every time we manage to organize. I think we already have a speaker for the next session of the PRIMO talk. Maybe we will announce him later because it's a him. But now I think it's time for Gianmarco to introduce today's speakers. So Gianmarco.
Thank you, Marco. Thank you. Hi, everyone. First of all, let me thank you all for being here today for this first PRIMO talk. It's my pleasure, I have to say, a great pleasure to introduce you, Elisa Riccietti. Elisa has been a brilliant PhD student at the University of Florence, dealing with Levenberg Marquardt methods for the solution of noisy nonlinear least squares problems. She gained the European doctoral thanks to a visiting period at INP IRIT in Toulouse, where she spent her her post-PhD studies under the guidance of Professor Serge Gratton. She has recently gained an associate professor position at the École Normale Supérieure in Lyon, and today she will be talking about second-order optimization methods for the solution of large-scale nonlinear noisy problems. So, please.
Thank you, Gianmarco, for this beautiful introduction. It's also a pleasure to have someone that introduced me pronouncing my name correctly. So I'm going to share my presentation. So I put it in large. Okay. So today I'm going to show you my work around the design of second-order methods for the solution of large-scale machine learning problems. So the problems we are dealing with are unconstrained minimization problems, especially we are going to consider least squares problems. And we are interested in problems that are large scale. So we have an objective function, capital F, that is defined from Rn to Rm. And the idea is that the problem is large scale because either m is large, so because the objective function f has a large number of components. This is the case, for example, when we have large data sets that we want to classify, or because f depends on a large number of unknowns, so in this case n is large. This is the case, for example, in the training of deep neural networks. So in both cases, we have a common objective that is exploiting some approximations to the objective function to reduce the computational cost of the solution. So I have worked on both problems. Previously, I've proposed some subsample methods for the case of M large. And more recently, I'm working rather on the case in which n is large. And for this, I've proposed some multi-level methods. So today I'm going to focus especially on this second case. So I'm going to present you a multi-level extension we proposed for a family of high-order optimization methods. And then I'm going to explain how we adapted a member of this family of multi-level methods to become a training method for artificial neural networks. And then I'm going to show how we can apply this training method to a specific application that is the solution of PDEs. So let's start with the high-order optimization methods we consider. So we are dealing with a general unconstrained optimization problem. And usually when we want to solve this using a second-order method, we are going to approximate the function in a neighborhood of the current approximation with the Taylor model of order 2. Then to compute a step, we would minimize the regularized Taylor model. So we are going to have a regularization term that depends on a regularization parameter lambda. And so classical examples of such methods are the trust region method, in which we have a quadratic model plus a quadratic regularization term, or the adaptive cubic regularization method, in which we still have a quadratic model, but the regularization term is of order 3. So what is the advantage of having a higher order regularization term? So the advantage comes when we consider the worst case complexity of the method. So the worst case complexity of the method is the number of iterations that are necessary in the worst case to reach a given optimality criterion. So in the case of unconstrained optimization, we consider as optimality criterion to drive the norm of the gradient below the given threshold epsilon. And so we wonder how many iterations we need to do that. In the worst case, it has been shown that for trust region methods, the complexity is proportional to epsilon to the -2, while for the adaptive cubic regularization method, the complexity is epsilon to the -1.5. So the complexity improves thanks to the use of a higher order regularization term. So in this paper here, the authors decided to propose an extension of the adaptive cubic regularization method, and they extended it to a family of higher order methods. So why to stop at order 2 if the derivatives are available? We can define a family that generalize this method, and so it's based on the minimization of a model that is given by the sum of the Taylor model of order Q, where now Q can be something larger than 2. And then we have a regularization term of order Q plus 1. So now the Taylor series is going to be defined in this way, where we are employing some tensor derivatives. And if we choose Q equal to 2, we recover the adaptive regularization cubic method. We can see, so the authors of the paper have proved that we can generalize the known result, the known complexity result for the cubic method, and we get actually this result. With Q equal to 2, we get the 1.5 that we have seen before. So the basic scheme of an high order method in this family is like this. So we define the model, then we have to minimize it to find the step, and then the rest is really similar to the classic cubic method. So we decide whether to accept the step or not. The step acceptance is based on this ratio, that is the ratio between the actual reduction that we get in the function and the reduction predicted by the model. If this ratio is large enough, it means that there is a good accordance between the function and the model, so we can accept the step. Otherwise, we need to increase the regularization parameter, and we need to solve the problem again. So in these methods, the bottleneck is really given by the minimization of the model. So this is the task, the most expensive task that has to be performed at each iteration. And the cost of this minimization problem really depends on the size n of the problem. So when n is large, this is really a difficult task. So that's why we have proposed a multi-level extension of these methods to leverage the cost of this subproblem. So our idea is the following one. So we are assuming to have a sequence of function approximations that are defined on spaces of decreasing dimensions, so that these function approximations become cheaper and cheaper to optimize. And then we also assume that at each level we have a model associated to the current function approximation. So the basic idea is this one. At the current iterate at level L, what do? Usually we would minimize the Taylor model to find the step. In this framework, we would rather project our iterate on a lower level. So we assume that we have at disposal some operators R and P that may depend on the level, and that allows us to move from one level to another. We can think of them as in the case of multi-grid methods. So these are the operators that allows us to pass from a fine grid to a coarse grid. For example, R can be a weighted operator, and the operator to go back can be an interpolation operator. So projecting the iterate, I get the starting point for the coarse level, and then I can employ the model available at level L-1. I can minimize this model, and so I get an approximate solution. So thanks to this operation, I have obtained a coarse step that is the one here in red, that using my prolongation operator, I can send back to the fine level. So the idea is that I have obtained a fine step in a cheaper way, because I have minimized my model at level L-1 that depends on less variables, and so it's cheaper to minimize. And also another advantage is the fact that the procedure is recursive, so we can employ more levels if they are available. So here, instead of solving this problem, I can employ the approximation on level L-2. So this is the basic idea of the method, and the general algorithm of the method would be something like this. So the scheme is really similar to the one we have seen before. The only difference is in the step concerning the model minimization. So here we can choose whether we use the Taylor model on the current level, or if we want to recursively adopt a lower level model. So the question is, how do we make such a choice? So the idea is that we have to employ the lower level model only if it is a good approximation of the upper level model. So the idea is that we have to check if the gradient of this coarse model is large enough compared to the norm of the function that the norm of the gradient of the function that I'm trying to approximate. And also we have to check that we have not reached optimality at level L-1. Then the other question is, we have assumed that we have this model approximating the function approximation at each level. How do we define such models? So the idea is that we define the model as the function approximation, but we had to add some term to allow, to ensure a coherence between the levels. So the idea is that, let's take the simplest example. Let's say that Q is equal to 1. In this case, we would add a linear term, a linear correction term, that basically depends on the difference between the projection of the gradient of the function at level L and the gradient of my function approximation. This is necessary because it allows me to establish this relationship. So I want that at least in my starting point, so in the point that I have projected, the gradient of my model is equal to the projection of the gradient of my upper level function. Why do I need that? Because this ensures me that if I have a descent direction for my lower level model, I also have a descent direction for the function that I want to minimize, so the function at upper level. Indeed, if I have computed this step, that is a descent step for my model at level L-1, I have this equality, and so I know that if I define the fine step as the prolongation of the coarse step, I'm going to have a descent step also for the function at upper level. So this is important to ensure the convergence of the method. and we can generalize it to each order. So if Q is equal to 2, we are going to add 2 terms because we want to ensure coherence at level. I mean, we want the function and the model to be coherent up to order 2 in this case, and so we can generalize this also up to order Q. So this would be the generalization. It's a bit more complicated because now this expression is involving some tensors, but we still have the difference. We have the sum over Q terms, and each time we have the difference between the projection of the tensor derivative and the tensor derivative at level L-1. And this restriction is defined in this way. So the idea is that the action on a coarse vector is the same of the action of the tensor gradient on a prolongated step. So regarding the theoretical results that we have proved for our method, to prove them we needed some assumptions. So the first assumption that we make is that the qth order derivative tensor is Lipschitz continuous at each level. This is a quite standard assumption in optimization, asking the Lipschitz continuity of the higher order derivative. And then we also have a more specific assumption that we use for the local convergence. So this is a sort of local error bound condition. So we are asking that we can control the distance of a point from the set of second order critical points of the function by controlling the norm of the gradient. This is a condition that is often used to prove local convergence results, but it's a bit different because usually we control the distance to the set of the first order critical points. This is a slightly different assumption that was introduced in this paper, where they prove local convergence of the cubic regularization method to second order stationary points. So under these assumptions, we have proved global convergence of the method so that we can reach a stationary point of F for any starting S. This result generalizes the results in the paper where the higher order methods have been introduced. So they are generalized to a multi-level framework. And this also generalizes the results in this paper where the authors proposes a multi-level trust region framework, but that considers just second order methods. And the theory is also really complicated. In our paper, the theory is much more simple. Then we have a complexity result that is really interesting. So the problem is again to count how many iterations we need to drive the norm of the gradient below a threshold epsilon. And we can prove that actually we can get the same bound that we have seen for one level methods. This is an important result because it tells us that at least in the worst case, we are going to need the same number of iterations than a one level method. So the number of iterations is not going to increase. And this is a good news because we expect our iterations to be less expensive thanks to the multi-level procedure. And so we can expect some gains in general. The last result that we proved is a local convergence result. And actually we proved that the rate of convergence of the method depends on the order of the method Q. So this actually generalizes the result that is proved in this paper to Q greater than 2. So we have implemented the method corresponding to Q equal to 2 and to Q equal to 3. And we have used them to solve some PDE. So here we have a PDE defined on a subspace of RD. We can formulate the problem as an optimization problem in this way. So A is the matrix that discretizes the Laplacian. And we can see that this is equivalent to this system that, that is the discretization of this problem. In this case, it's really easy to build the hierarchy of problems because we just take coarser and coarser discretization of the original infinite dimensional problem. This is just as in standard multigrid methods. So here I report the results for a 1D problem that we have solved with the method of order 3. So here I am comparing the standard one-level method of order 3 with our multi-level method of order 3. This is the size of the problem. So the full size of the problem, yes. Yes, so this is the size of the problem. And this is the starting guess. So in this first case, I've taken a starting guess not too far from the true solution. And I am reporting the total number of iterations and the total number of iterations that we have performed at fine level. So we can see that for our method, we really need to do few iterations at fine level. All the other iterations are done at coarse levels. And here I report the savings in terms of computational time. We can see that this is really the CPU time. We can see that the savings increase when the size of the problem increases. And then we can see that we have also more important savings when we take an initial guess that is farther from the solution. So the method is indeed effective. And now I'm going to present how we can use all of these in a more practical framework, so in the training of artificial neural networks. So the idea is that when we have a network with a lot of weights, with a lot of nodes and so a lot of weights, we are going to have a problem where n is large. So it is it could be beneficial to use a multi-level method to speed up the training. Then the question is, how are we going to build a hierarchy of problems? Because in this case, it's not so simple as in the case we have seen before, because in the case we have seen before, we are dealing with a physical problem that has a proper geometry. So it's easy to build a hierarchy because we are discretizing a problem on a grid, on a physical grid. And so we know how to take coarser and coarser grids. In this case, it is not clear how we could do because the variables that are subject to the optimization problems are the weights and the biases of the network that does not possess an evident geometrical structure. So we expect that we cannot use classical strategies also to move from a level to another. But yet the network has a structure, even if it is algebraic rather than geometrical. So maybe we can exploit this structure to build the hierarchy. So our idea was indeed still to refer to classic multi-grid method, but we decided to use some technique coming from algebraic multi-grid method. So these are techniques that are used to solve large-scale systems arising from discretization of PDEs. And the idea is that these methods are capable of building a CF splitting, so meaning that it's capable of splitting the variables into two sets, a set of fine variables and a set of coarse variables. So the coarse problem will involve only the variables in the set C, while the fine problem will involve the variables in the set F. And this splitting can be built just looking at the entries of the matrix. So we don't need any underlying geometry, we just need to know the matrix A. So in this case, also the hierarchy is automatically built, and also the prolongation and restriction operators are built in this way. So the prolongation operator will be the identity for the variables in the coarse set. So they are going to be also part of the fine set. And the other variables are going to be a linear combination of the coarse one. And then the restriction operator is, as it is common in multi-grid methods, is the transposed of the prolongation operator. Then this is a technique that is used for the solution of linear system. We are dealing with an optimization problem, so we don't have a linear system to solve. So our question is which kind of metrics should we consider to apply this technique? So our idea was, of course, to apply it to the metrics of second order derivatives. So usually, if we consider a second order method, we are going to have a model of this type, where BK is an approximation to the Hessian matrix. And so at each iteration, we have to solve a system of this form. And so we decided to apply the AMG technique to this matrix BK. Then, of course, doing this is expensive. So in practice, we have seen that we can do this just once at the beginning of the optimization process. So we don't do it at each iteration. But again, we have to be careful because we cannot directly apply the technique to the full matrix BK, because actually the variables are coupled. We have to consider that we are dealing with a network, so variables are not independent, because, for example, I cannot remove this edge if I keep, if I remove this edge, I will need also to remove the corresponding node, so the bias, and also the input weight, because otherwise I'm going to obtain a network that is not coherent. This is not well connected. So instead of applying the technique to the full matrix, we consider matrix A, that is a weighted sum of the sub-blocks where I consider derivatives with respect to the same kind of variables. So in this case, in this way, I avoid a network like this. Okay, now I'm going to show you how we applied this multi-level technique, this multi-level training technique to a specific problem that is the solution of PDEs. This is actually a topic that is really not topic nowadays. There are a lot of really recent papers on the topic. And the reasons behind this is that actually using an artificial neural network to approximate the solution of a PDE has some advantages over classical approaches. For example, this is a natural approach when we want to solve nonlinear equations, because the neural network itself is a nonlinear model, so we don't need to linearize. So we don't need to approximate anything, we just can use the model directly as it is. Then another advantage is that we know we have an analytical expression for the output of the network, so we are going to have an analytical expression for the approximate solution of the PDE. This is useful, for example, in some applications in which we want to compute derivatives of the solution. Another point, good point, is that the solution is meshless. So we don't need to build a mesh to find the solution, but we just need to be able to sample the domain of the PDE. So this is good in the case in which we have problems defined on difficult geometries with many edges. So in cases in which building a mesh is complicated. Then, of course, the training is highly parallelizable on GPU. And maybe the most important point is that it has been shown that with the neural network approach, we are able to alleviate the effect of the course of dimensionality. So the problem is that when we are solving PDEs in high dimensions, we are going, so the number of points that are necessary to sample the domain will increase exponentially for standard methods. And it has been shown that this is not the case for methods based on artificial neural networks. So this is a huge advantage for problems in which we really have high dimensional PDEs. This is the case, for example, in economy, in which we have stochastic equations that have a really high dimension. So just to explain the approach, we consider a simple 1D case. We have a differential operator D, and we have some boundary conditions. So the idea is that we are going to use a neural network that will approximate the solution of our PDE. So the idea is that the neural network takes Z, that is the geometrical variable of the problem, as an input, and then it gives an approximation to the solution of the PDE that depends on the weights and biases of the network. Then to choose the good parameters to approximate the solution, we need to define a loss function and to have a training procedure. So our idea was to define the loss function as this function here, that is the sum of two terms. So here we consider the equation residual. So we consider some points zt in the interval in which the PDE is defined. And then we consider the nonlinear equation of the residual in these points. And so we build a large vector of residuals. And then we add a penalty term for the boundary condition. Lambda p is a penalty parameter. So in this way, we end up with a least squares problem. So we decided to solve it with a multi-level Levenberg Marquardt method. So the Levenberg Marquardt method in its classic form is a method that is usually used for the solution of least squares problems. And the idea is the following one. We have our objective function that is the norm of capital F. And we get a model for our function small f by taking the norm of a linear approximation of the function capital F. In this way, we get a quadratic model for the function small f with approximated Hessian. So BK is our matrix J transpose J, where J is the Jacobian matrix of capital F, and this is an approximation of the Hessian of F. Then the rest of the procedure is as in the algorithm we have seen before. So we decide whether we want to accept the step or not, and we update the regularization parameter. So we have used the multi-level extension of this method to solve the Poisson equation. This is a 2D equation. The size of the problem is this one. And here, what I'm doing, I'm solving the problem. So I'm approximating the solution of the PDE with a neural network, and then I'm training this neural network with ADAM, that is a first-order method that is currently used in many machine learning libraries. And then I'm using the classical one-level Levenberg Marquardt method. So we can see that, of course, the Levenberg Marquardt method converges in far less iteration than the ADAM method. But if we look at the computational time, we can see that there is not really a big advantage in using the second-order method because we do less iterations, but they are more expensive. So we don't have any gain. Then it's really interesting to use a multi-level approach because we can see that the number of iterations does not change, but we have a really important gain in terms of computational times because the iterations of the multi-level procedures are less expensive. So at the end, we get a gain with respect to classical and well-known first-order methods used in machine learning. So these are just some results on more difficult domains. So the first one was just Poisson equation, so it's really simple. And here we have some results on also nonlinear problems that are defined on more particular geometries. And so we show that even if the geometry of the problem is more complicated, we can get good approximations, and we still have good savings with respect to the standard Levenberg Marquardt procedure. So to conclude, in our work, we have proposed a family of multi-level high-order methods, and we have proved some theoretical results, so global, local convergence, and complexity. And then we applied these multi-level methods to the training of artificial neural networks. And then we applied these methods to a problem that is currently being studied a lot in the machine learning community, that is the solution of PDEs. So regarding the perspectives, the main problem with our approach is that we are still relying on the Hessian matrix. So this is good for problems that are not too large, but when n really becomes large, we cannot employ this procedure, because especially the main problem is that we need the Hessian to compute the hierarchy of networks and to compute the operators to move from a level to another. So if n is really large, this is clearly not possible. So a possible idea is to use a different kind of network. So in this case, we have used feed-forward networks. Another possibility is to use a ResNet network. Why? Because actually the interesting thing about these networks is that the propagation of an input through the network can be expressed by a formula like this, where f in this case is the result of the application of the sigmoid function and the application of the bias. I mean, it's just the propagation through the network. So this can be seen as a one-step method in which we have chosen delta t equal to 1. So actually we can think of this as a discretization of, thanks to a Euler method, of this one value, initial value problem. So this is an interesting interpretation because it gives us an underlying problem that can easily be discretized on different discretization levels, and in this case the time step will correspond to the number of layers in the network. So this is a really nice idea because it gives us a natural way to build a hierarchy, and so from here we could build maybe an Hessian-free method. So for the moment it's just an idea. We didn't do anything for the moment. So thank you. These are the publications related to this work if you are interested in more details. Thank you.
Thank you so much, Elisa, and any comments or questions are welcome.
I will have two questions actually.
Yes, for sure.
Can I, or do you want to collect them, or can I ask already?
You can ask directly. You can unmute yourself and ask.
Okay, so thank you. So I'm Gabriele. I'm from Fondazione Bruno Kessler. So first of all, thank you for the very nice talk. It was really interesting. And I mean, the first question is on the application to the optimization of neural network. So did you try to, so at the end of the day, you're trying to solve a problem, an optimization problem, but at some point it may become too large, right? So that what you mentioned at the end, that you need the Hessian and that is not working if the problem is too large. And do you think it's possible to apply your method in combination with some mini batch strategy? So usually in neural network with stochastic gradient descent, so what is done is that usually you restrict the optimization problem to a small subset of the data, and then you solve the small optimization problem associated to only those samples. To the mini
yes, sure, you can do that, but I mean, this is going to affect the number of components in your objective function. So it's not, I mean, this is more on the output. Imagine at the beginning, I introduced this function capital F that is defined from Rn to Rm. So the batch strategy is going to affect the output space. So this variable m, not the size of the input space n. So of course you can use them in combination, but this is the batch strategy is not going to be useful when n is really large.
Okay, thank you. And can I ask a second thing?
Sure.
So the other thing is about the solution of PDEs. So there is, I mean, I find it interesting at least. So the field of parametric PDEs and model reduction. And in that case, you need to solve a lot of PDEs where there is a dependency on some parameter. And the parameter changes the solution, but maybe not so much, let's say. And it is interesting to find strategies that make it possible, let's say, to compute a solution for different parameters without recomputing everything from scratch, let's say. And do you think it's possible to adapt your technique to, I don't know?
that case, I mean, you can train the network and then start from the solution that you have found to as a starting point for the next.
Okay, I see. Okay.
Because also you can, there are applications in which rather than looking for the solution of the PDE, you can also find the parameters on which the PDE depends. So I mean, if you have a parameter in the PDE, you can learn also the parameter of the PDE. I don't know if it is.
That's the question. Yeah. Okay.
Yes.
So, but thank you for the answer.
It's easily adaptable. Yes, you just have to change the loss function.
Okay. Thank you, and thanks again for the nice talk.
So, any other question?
Oh, I have one, Elisa. It's Benedetta. May you give me more hints on the network you trained for solving the PDE? I mean, how do you design the network? May you go to the slide where you show?
It's charging. Okay, this one.
Oh yes, and then the problem. Yes, thanks.
So regarding the network architecture, in the tests that I have shown, we have just used a network with just one hidden layer. So our idea was that usually they say that, I mean, there is a theorem that ensures us that a swallow network with a lot of neurons in the hidden layer has the same prediction capability of a deep network. The only problem is that the number of parameters can be too large to have the same performance, and maybe the network with more layers are easier to train. So our idea is that if we have this strategy for which we can reduce the number of neurons in a layer with this hierarchical structure, why not to simply use just one hidden layer? So we can allow more neurons that we would usually do, and then we just reduce them with our multi-level strategy. So this can be thought as an alternative approach to having a really deep network. So from the tests, this is the only architecture that we have tested in practice.
Okay, so ZT means that you have capital T.
ZT is related to the physical domain of the PDE. So let's say you have a PDE defined in 0, 1. You take some, in this case is capital T points. We have taken them X-spaced points in the interval. And so you are going to evaluate the, maybe here we have a little point that maybe it was a little fast, because here I have a differential operator. So let's say that D is the Poisson operator. What we are doing is applying the differential operator to the output of the neural network. So I know the analytical expression of the output of my neural network because it is going to be the sum of the activation functions in which I take into account all the biases and the weights. And so this is an analytical function that I can derive. So I can compute first order derivatives, second order derivatives easily.
Okay, I see.
And so this is this function evaluated in these points in the interval.
So ZT are grid points?
Yes.
Okay.
Physical points, yes. And so I have a long vector in which in each component I have applied the differential operator to the output of the network, and then I have evaluated it in the specific point. So this is also because we decided not to make the assumption that we have some measurements, because there are also other papers in which they rather assume that they have the solution of the PDE evaluated in some points of the domain. And so in that case, the training problem would rather be like the standard least squares criterion in which you try to fit the measures.
Okay, thank you very much, Elisa.
So Elisa, what you mean by complexity is iteration complexity, really, and it's related to the number of external iterations of the method to reach a critical point for the first time in the worst case. But complexity of inner procedures, such as minimization of the subproblem, would affect the final execution, especially for high order methods. Do you think that an investigation of total complexity could in practice limit the use of high order methods? It's just...
I mean, it would surely be interesting to study this. Then, but of course, minimizing an higher order model is more difficult than minimizing a lower order.
Orders, yes.
But we have, I mean, I actually implemented the third order methods. It's performing quite well. I mean, we get good solutions in not too long time. Then, of course, I think we have to couple it with an inexact minimization of the model, because otherwise, sure, it's going to be really expensive. So in thinking to a big data regime, we really need to have an inexact method.
Yes.
That would help complexity.
So, yeah, so to reduce the per iteration cost. Okay, thank you. We have time for the last question.
I have one, but I would like to see if anybody else in the Zoom room has another question. So I can always contact Elisa separately, maybe. But if nobody else would like to have a question,
Excuse me, can I ask a question?
Yeah,
sure.
Go on.
Thank you, Elisa, for your presentation. Thanks a lot. In initial slides, you mentioned from higher level to lower, you used a projector, R, if I'm not mistaken. Yes. I'm interested to know what's R. Is nonlinear projector or linear one?
So in the case of, so when I have shown the first numerical tests, this is just the standard weight operator that we use in the multi-grid methods. So we just take, I mean, if we have some fine points, we do a linear combination of them and we get the coarse points. Because in that case, we have a physical grid, so we can do that. Otherwise, in the case of the neural network, the operators directly come from from this strategy, so from the algebraic multigrid strategy. And actually, the algebraic multigrid strategy builds the prolongation operator that is really defined as a part is the identity matrix, another part is some matrix delta that is defined. I mean, I can maybe have a backup slide where I show how this matrix is defined, but this is just a linear operator that gives a combination of the coarse variables to give to obtain the fine ones. And then the restriction is just the transpose of P. So they are all linear operators in every case.
Okay, many thanks.
So Marco, would you like to ask your question?
No,
just to conclude?
I don't know, it's late. People maybe need to go back to the duties or maybe go back home.
Marco,
Dani.
and Daniela. Hello, Elisa.
Hi.
A very quick question. Maybe I missed something. Just a curiosity. When you go back from the coarser level to the finest one, of course you use a prolongator. Yes. Or usually when you apply multi-grid or multi-level strategies to PDEs or even to the solution of linear systems, you must be very careful because spurious components may arise. And this is the reason why you need what is called usually a relaxation, post-relaxation. I didn't understand if after, okay, you solve the problem, you go down and down toward the coarsest level, you solve the coarse problem. But when you go back to the initial solution, what do you do in practice? I didn't understand. Are you applying simply a correction? Are you doing something else? Because usually in multi-grid methods, you need to do something else, because when you interpolate, essentially, going up, spurious components may arise that may perturb what you got going to the coarsest level. I didn't understand if you are doing something like this, or you don't need this in your approach, because you are doing something different. Of course, you are working in the area of the optimization, so maybe it could be completely different.
I think I mean, the idea of multi-grid in optimization is not new. So this is something classical. We just maybe what you say is avoided by the correction term that we add in the model, because here we really do this. I mean, here we are at the current iterate, we project it, then we have our course problem, so we solve possibly approximately, and so we get a course step, and then we just project it onto the fine level. So we define the fine step as the prolongation of the course step.
So the prolongation simply gives you a correction term, but you don't know anything else. This is what I wanted to understand. So you you restrict your problem, you solve, and you go down and down until you reach the coarsest level. Yes. Then you get a correction, and then you prolongate that correction across all the levels, but you simply add the correction, yes. But you don't need anything else. And do you know, can you say something? Of course, you have all the theoretical results, the practical accuracy that you experienced in this, because with PDEs or with linear systems, this is a non-negligible task. You need to correct, but you also need to perform some smoothing. It is called smoothing, just to try to attempt to eliminate the spurious components, the spurious that may arise. So I just wanted to know if you observe the same thing in optimization, because I know that this idea is pretty old in optimization, but if I'm not wrong, it was, there were some papers maybe 20 years ago, and then the idea was a bit abandoned because it was not, so I just wanted to know what's the accuracy that you can expect from this.
I have not seen this smoothing term in nonlinear optimization. Then my experience from practical use of the method is that I always get the same accuracy that I get with the one level method in approximately more or less the same number of iterations. So maybe we don't have this issue in, so for example, in the results, maybe, yes, it's not present in the tables, but here I'm using the same stopping criterion for the two methods, so the one level and the multi-level, and also the accuracy on the solution is really the same. So I don't observe a lack of accuracy. And also in these cases, I was I had quite accurate solutions. Then maybe this problem is also less important in machine learning applications, because there we really look for an approximation to the solution. So we are not really going to reach really good accuracy as we would with a direct method. But also because, I mean, it's really difficult to beat direct methods, standard direct methods for PDEs. If you want
of
to,
course,
this is not something.
No. But of course, I don't think that your goal is this yes, one. I think that your goal is completely different, because I don't think that you can beat any standard method for PDEs, at least at this stage. But I was just curious, because I wanted to know if you observed something strange, which appears if you deal with the linear systems in an algebraic manner, or if you deal with the PDEs directly. Because
in the comparison, I really observed the same behavior,
more or less. Okay.
Yes.
Okay.
Actually, in some tests, the fact of using a multi-level framework helps the convergence. So sometimes I can avoid some local minima and I get even a better solution with respect to the one-level method.
Yes, this is not a surprise because at least in PDEs, when you change level, in some sense, you make the problem smoother and smoother.
Yes.
Okay, so probably, but this is just a guess because I have no experience in that. Maybe it would be nice to analyze the shape of the function that you get on the different levels to see if maybe wiggles or local minima become, the function becomes smoother and then local minima disappear, for example. But I don't know, actually, I don't know. It was just a curiosity. Thanks a lot.
Thanks.
Yes, I was muted. So, okay, thanks, Daniela, for your question. Thanks, Elisa, for your talk, for the nice chat which followed your talk. I think now it's 6 p.m. in Lyon, and it's time to say goodbye to you and to all the people who attended this first PRIMO talk today. I would like to thank everybody and just tell you that the next PRIMO talk is already scheduled. It will be on October 29th. It should be a Thursday as well. And the speaker will be Santoro Levesque, which is a doctoral student at the University of Edinburgh. So thanks a lot again, Elisa, and to everybody.
Thanks a lot for the invitation.
Have a good evening.
You too.
Bye.
Thank you. Bye. See you.
Ciao Elisa.
Ciao. Grazie di essere venuti.